So now we'd like to take an opportunity to use some of the information that we've learned about P-series to apply it to other series to try to determine whether they might converge or diverge. So what I'm going to do is I'm going to list several several series, and I'm going to ask you to think about for a moment whether you think these series might converge or diverge. And as you're thinking about this, try to put it in the context of the information that we know about P series. So here are a few series. I'm going to call, let's see, series A. Let's let that be the sum from 1 to infinity of 1 over, say, 3 plus n squared. Let B be the series that, again, will go from 1 to infinity. This time we'll consider n plus 1 over 2n minus 1. Series C, let's let that be the sum from n equals 1 to infinity of 1 over, how about 3 plus 10n. Come over here in series D. We'll let that be the sum n equals 1 to infinity of, let's let each term be 1 over n squared minus 3. Actually, starting at 1, we'll make some of these negative. Let's start this one at 2. Let's let n go from 2 to infinity. And then series E, let's consider the series n equals 1 to infinity of 1 over 100n minus 1. So just take a look at those for a moment, and I'd like you to copy them down and then pause the video for a while until you've had an opportunity to think about these. And I'll see you back in just a moment whenever you, after you've had a chance to think about these. Okay, so now that you've had an opportunity to think about some of these, let's talk about some of them together. First of all, let's go back and look at the very first one that we've considered. Let's see. So series A. So we're going to look at series A here. What we notice, especially whenever we're thinking about putting this in the context of some of the P series that we've looked at before, is that the terms of the present series look very much like the terms of the P series, except the denominators are a little bit bigger. Well, big denominators make for small fractions, and so what we have is that each one of these terms, 1 over 3 plus n squared, these are all smaller than the corresponding 1 over n squared. What we'll see, and we'll give a solid argument for this in just a little while, what this means is that since the P series with P equals 2, the series with 1 over n squared is the terms, since that converges, remember, a P series converges provided that the exponent is bigger than 1. So since this series converges and the terms of the series in question are all smaller than the terms of this series that we know converges, well, if these terms were small enough to converge and these are smaller still, then we expect the series in question is going to is going to converge. And that's exactly what happens. All right, so we're in that situation. You may have guessed that. And if you thought that through in that way, then congratulations. You're absolutely right. Now, series D over here also looks very similar to the P series 1 over n squared. Terms are 1 over n squared. The problem with this one, we can't use this argument that we use down here on this series, because as it turns out, the terms of this series, well, the denominators are smaller, which means that the fractions that we're looking at, the terms, are actually larger than the terms of the corresponding P series. Well, knowing that the P series with the terms 1 over n squared converges no longer says anything about what this is going to do, right? 1 over n squared was small enough for the terms, gave small enough terms for the series to converge, but these are larger. So that doesn't say that these terms are going to be small enough for the series to converge. So we can't use this argument for series D, and we're going to have to think about that a little bit differently in just a bit. Similarly, if we were to look at the series C here, let's think about that. Series C looks like, well, let's take a look. So C has the terms 1 over 3 plus 10n, and is running off from 1 to infinity. And 1 over 3 plus 10n is, well, let's see. This is my denominators are larger than the denominators 1 over 10n. And so large denominators make for small fractions, right? So I have this relationship going on. And of course, 1 over 10n is just 1/10 of 1 over n. So this looks like, on the surface, it looks like we could compare this series to the harmonic series, or 1/10 of the harmonic series. Of course, 1/10 of a divergent series is still going to be divergent. Problem is, these terms are smaller. These terms are smaller than the term. So these terms are too large to give us a convergent series. These are smaller, but that doesn't tell me that they're smaller enough. Maybe they are, maybe they aren't. But we run into a similar problem here that we ran into with our 1 over n squared minus 3 series, comparing it to 1 over n squared. We're running into it in the opposite direction. Remember, in this case, we run into a similar problem as we did whenever we tried to use the P series 1 over n squared to compare to this one. The terms here are they're larger than the terms of a convergent series. They might be too large. We don't know. Here, we're looking at terms that are smaller than the terms of a divergent series. Maybe they're small enough to give us a convergent series. Maybe they're not. We don't know. So we're going to have to come back to this one a little bit as well. However, series E suits us very nicely. Series E looks very much like, again, the harmonic series, or it looks like 1/100th of the harmonic series. And so let's take a look at this. So these terms, let's see. So these are, the denominators are small, which means the fractions are big. These are bigger. than 1 over 100n. And of course, 1 over 100n, that's just 1/100th of 1 over n, right? So the series, the harmonic series, or 1/100th of the harmonic series, that's going to be divergent. These terms are bigger still, right? So the terms of the harmonic series are too large to converge, and these are larger still. And so since our series 1 over 100n from n equals 1 to infinity, let's see, that would be the same as 1/100th of n equals 1 to infinity of 1 over n. Since that diverges, and the terms of the series that we're interested in are larger than these terms for each n, we have that the series in question is also going to be divergent. Right? And so the general principle that we're seeing is the following one. So in general, if I've got a series that is convergent, and I have some other terms bn, where each bn is less than or equal to an for each n, and all of the ans and bns are positive, or at least non-negative for each n, then the bn series is also convergent. Right? So again, if I've got a series for which the terms of the series are small enough to give me a convergent series, and I have another series whose terms are smaller still, then those terms are all going to, or those terms are going to be terms of a series which is also convergent. Now, it is important that all of the terms that we're looking at are positive in this test, and we'll see why whenever we write out a little proof of it here in just a little bit. This is called the direct comparison test. And turns out to be a very useful test. It's also one that makes a whole lot of sense. Actually, this is part 1 of the direct comparison test. Part 2 is similar, and it says that if I know that my AN series is divergent, and each of my ANs is less than or equal to my BNs, and again, I need for all these to be positive terms for each n, then, well, what do you think? The BN series? So again, so my ANs are too large to converge, right? They're so large that I wind up with a divergent series, and my Bn terms are larger still. So my Bn series is also going to diverge. Right. So these are the two parts of the direct comparison test, and we'll be using those frequently. Now I want you to think again for a moment. What was the mantra for this chapter? Now, it began, well, it's the mantra. Our mantra is the statement that tells us when how we know that a series is convergent. Right? It begins if the sequence of. I'm going to stop there for just a moment. I want you to think for a moment, see if you can bring it back to your memory. You have it? Okay. So mantra for this chapter is if the sequence of partial sums of a series converges, then the series itself converges. All right, I'm going to write that down again. It's very important to what it is we're going to do in order to prove the direct comparison test, to give something a little bit more rigorous rather than just the kind of the hand waving argument that I gave here. So mantra for the section, mantra for the chapter is if the sequence of partial sums of a series converges, then the series converges. Okay, so we also saw in a previous lesson that if a sequence is both bounded and monotonic, then the sequence converges. All right. Now our proof for the direct comparison test, and I'm just going to prove part one here. So we're going to do that by showing that that if I look at if I have a convergent sequence and I have another, convergent series, beg your pardon. If I have a convergent series and I have another series whose terms are smaller, what I'm going to show is that the sequence of partial sums of the Bn series is both bounded and monotonic, right? Because if I can show that the sequence of partial sums is both bounded and monotonic, then the sequence of partial sums is going to be convergent. But if the sequence of partial sums is convergent, then the series itself converges. So that's basically the argument. So the proof of the direct comparison test, part one, goes something like this, right? So if so we're going to suppose that I've got this series AN that's convergent, and also suppose that we've got another series. I'm going to indicate the terms with Bn, and all those terms are less than or equal to the ANs. And again, this is going to be very important. All of my terms are non-negative for each N. All right, so what do we have? Well, so start with B1 here. B1 is smaller than or equal to A1. And of course, A1 is going to be smaller or equal to adding all of the A's together. Right? Again, all these A's are positive, the ANs are all positive. And so whenever I add them all together, I get something that's going to be no smaller than A1. Well, similarly, B1 plus B2, well, that's less than or equal to A1 plus A2. And that's going to be less than or equal to all these guys. And in fact, well, I could do this forever. For every N, right? So B1 plus B2 to Bn. So this is the nth partial sum of our Bn series. That's going to be less than or equal to whatever this number is that the ANC series is converging to, right? And since all of these B's are all positive, when I start at B1, since B2 is positive, this is a larger number than B1 was, or at least it's no less than B1. The next partial sum is going to be larger still. And so this sequence of partial sums forms, well, a monotonic sequence. It's increasing. More than that, every one of these terms, every one of these partial sums is bounded, right? They're all smaller than this. So the sequence of partial sums of this Bn series is monotonic. It's also bounded, right? And so the sequence of partial sums of my Bn series is monotonic and bounded. And therefore, it converges. Whenever I say it, I mean the sequence of partial sums converges. But back up here, the mantra says if the sequence of partial sums of a series converges, that's what it means for the series to converge. And that's what we needed. Therefore, the Bn series converges. Nice little proof. I think it's very understandable. And I hope that you will learn to be able to carry out that argument and explain it to others if need be. Now, this still doesn't answer the question about what to do with series like this and series like this. Remember, the temptation is to compare it to 1 over n squared in this case, but these terms are larger than the 1 over n squared terms. Maybe they're too large to give me a convergent series. Maybe not. Similarly, down here, temptation is to compare it to the harmonic series, or 1/10 of the harmonic series, which is divergent. But these terms are smaller. Maybe they're small enough to give us something that converges. Maybe not. But we're going to have to give a different argument and a different test for series such as those. And that's what we're going to do next. Bring out a clean sheet of paper here. And let's start by considering one over n squared minus 3 as n ranges from, and again, just to keep them all positive, we'll start at 2, go up to infinity. What I'm going to do is give you the technique that we're going to use, and then we'll explain to you why that technique works. We are, in fact, going to compare this series to the P series with p equals 2. We're going to compare to this series that we know converges. But we're not going to use the direct comparison test in order to do this. Starting at 2 here. But we're going to compare it in a different manner. And at first, this is going to look bizarre. So here's what we're going to do. I'm going to look at the nth term of the series in question. Right? So 1 over n squared minus 3. And let's let Bn be the nth term of the P series that we're going to compare it to. And then we're going to consider An over Bn. And let's see, what is that? So An is 1 over n squared minus 3. Bn is 1 over n squared. We can simplify that a little. This is 1 over n squared minus 3 times what? N squared over 1. All right, which is what? N squared over n squared minus 3. And what we notice is that as n rounds off to infinity, this quotient, this An over Bn, is, well, let's see. So n's rounding off to infinity. That quotient was equal to n squared over n squared minus 3. Could use a little algebra here. We could use Bernoulli's rule. Either way, we can see in a couple of steps that this limit's going to be 1. And what's important about 1 for the purpose of this test is that it's both finite, right? It's not infinite, and it's positive. Now, the terms were all positive, right? In both of our series, these are always positive terms for n. So we're starting at 2. So whenever starting at 2, these are all positive terms, and so the limit's guaranteed not to be 0. I'm sorry, guaranteed not to be negative, but it could have been 0. It wasn't, right? And it was finite, and it was also positive. So what this means is that this is a number. Let's see. So this means that for large n, An over Bn is about equal to this finite and positive number, 1 in this case. I'm going to change 1 to, I think we're going to call it L for now, just to remind me that that 1 was an important, the fact that it was finite and positive was the important thing. Right, so for large n, An over Bn is pretty close to this number L, which means that An was pretty close to L times Bn. which means that the series of ANs, n equals 2 to infinity, is pretty close to the series L times Bn, which that L is a constant. I can factor that out. And I've got something that looks like this. Right, so what I have is that since this is pretty close to that, since this converged, this is going to converge also to something that's about, not exactly by any means, but about L times this series. So this series is going to be what, about 1 over L of that series. Well, that's convergent, right? So because this series converged, comparing it in this way tells me that this series converges also. Now, this is a little bit of a hand-waving argument, and we'll put a little bit more rigor behind that in just a moment. But we'll notice that this same argument can be used for the other series as well. Let's see, what was that other series? So that other series that we were looking at was this one down here. 1 over 3 plus 10n, right? That's the one we said we were having problems with. No. Right, I'd like to compare it also, compare to, let's compare to the harmonic series. And we'll do exactly the same thing. We'll take these terms, 1 over 3 plus 10n, maybe call those my ANs. I'll let my BNs be the terms of the series that I know something about. And it doesn't matter which of these I choose to be which. No matter at all. If one gives me something that's finite and if one gives me quotients that's finite and positive, then if I looked at the reciprocal of that, I'm also going to get something that's finite and positive. It's going to be 1 over L. Doesn't matter. Finite and positive is the important thing. Going to look at the quotients. And I get, let's see, I'm going to get 1 over 3 plus 10n divided by 1 over n, which is the same as times n over 1. And so whenever I look at the limit, n equals, or n goes to infinity of an over bn. All right, so this is going to be the limit as n runs off to infinity of n over 3 plus 10n, which after one application of Bernoulli's rule, or if I divide top and bottom by n, I can get it that way as well. Either way, this limit is 1/10. 1/10 is finite and positive. And so really for the same reason that we talked about up here, right? So in this case, I have that this series is about equal to that series, right? But my 1 over n series, in this case, diverges. So this is a divergent series. And L times a divergent series, right? 1/10 in this case, times a divergent series, it's still divergent. So this is a divergent series. So either way, I can use this test, or I can test it on against a series which I know converges. If I want to try to show that the series I'm working with is convergent, right? Or I can compare it to a series that I know diverges if my goal is to try to show that this series is a divergent series. And so with this example down here, since I know that my 1 over n series diverges, so does So does my 1 over 3 plus 10n series. Right, and this is true by what we call the limit comparison test. Right, I'm taking limits here. I'm taking limits of these quotients. So I'm comparing one series to another by looking at the quotients of the individual terms and then looking for the limit of those quotients as n runs off to infinity. And so this is called the limit comparison test. All right, and so let's state the limit comparison test just a little bit more concretely. So let's let n 1 equals n equals 1 to infinity and bn n equals 1 to infinity be series with positive terms. So 0 is less than or equal to all of my an's, and 0 is less than or equal to all of my bn's. If the limit as n runs off to infinity of the quotients an to bn is both finite and positive, then either both series converge or both series diverge. And that's the limit comparison test. And I'd like to give a little proof of this. I'm going to prove the case first whenever my whenever one of my series is known to converge. So do a little proof. So let's suppose that my AN series converges. And we'll also let this limit n runs off to infinity of an over bn. We'll call it L. And let's let it be both finite and positive. Okay, so what's that say? So if I'm looking at my an over bn's, so call this L right here, and an over bn is, well, it has limit L, and so that means that these guys are going to be really close to L eventually. Right? So they're all going to be in here someplace for large enough n. Right? And the fact that this limit is positive, right? It's non-zero, means 0 is down here someplace. Okay, so 0 is down there someplace. So what's that say? Well, for these guys, right, again, for whenever n is large enough, I have that an divided by bn is actually, what I'm going to do is, since these guys are all near L, which is bounded away from 0, there's going to be some number down here. I don't know, call it maybe L prime. That I can definitely say that these guys are bigger than this number L prime. For large enough n. Well, so what? Well, that means that a sub n is going to be larger than L prime times b sub n for large enough n. Right? And right, so what does that mean? Well, written another way, it might be easier to look at this way. I have that 0 is less than or equal to this L prime times Bn, which is less than An. Well, the An series converged, right? Ans were small enough to give me a series which converged. That's what I was assuming. These terms are smaller still. And so we can go back and use the direct comparison test on the series that have these terms to conclude, right, these 3 dots together means therefore, to conclude that since the An series converges, that this L prime times Bn series also converges. And that's true by the direct comparison test. Right, so we used the test that we've already proven in order to prove this new one, in order to prove the limit comparison test. Well, if this series converges, then the Bn series must also have converged, right? I can factor L prime out of every one of these terms. And I get the series written this way. And so this series must also converge, because L prime times a divergent series would have diverged, right? So this must converge also. What I'd like you to do is to try to take this argument and refashion it to show that if my An series diverges, then the Bn series diverges as well. I'm going to leave that one up to you. See if you can figure out how to give an argument for that proof. It's going to be very, very similar. And with that in mind, this is going to end our lesson on the direct and limit comparison tests. Homework is posted on Canvas, and I will be posting solutions to the homework as well on Canvas, just as if I were in the classroom posting them around the room. No souvenirs this time, however. Actually, I guess you could print them off for yourself, but you'll be using your own paper. Thank you for listening. I look forward to seeing you next time, and stay safe, stay healthy. Take care.